Okay, so I just want to make sure that you guys can see what I think you can see. All right, so I'm a person that really likes model kits, and this particular one I think is really cool because all the parts are magnetic, so they all stick to each other, which is really nice because if you've played with them before, a lot of them you have to physically connect them, but these just kind of click together, and I think that that's kind of fun. So what we're going to do is kind of walk through some ideas here. You guys already know that the way that we do a lot of things in our class is related to sort of the order that things were discovered by real chemists in the real world. So I don't start with theoretical stuff. We're going to start with things that we can measure and identify and talk about, and that's how this part's going to go. But we're going to start to get the things that kind of feel a little bit more abstract because we have to start figuring out how reactions work, and that's kind of tricky. So up at the top here, there's some notes about, hey, you remember when we did that thing called the ideal gas law? You guys remember Pivnert? All right, so our relationships with Pivnert said that pressure and volume equals the number of particles times the ideal gas constant times temperature. And so when we look at this part one here, we've got two boxes. And what this says is what's reasonable to conclude about the number of particles in each container if the pressure and the temperature is the same in both containers. It's also telling us a little bit farther up here that when the volume and the number of particles are held constant, then pressure is going to be proportional to temperature. So we know that too. But what ends up happening down here is that if our pressure is the same and our temperature is the same, that if we have the same volume, we can infer that we have the same number of particles. So I think that we can agree that trying to count the number of particles in a sample would be pretty tricky. But if the pressure and the temperature and the volume are the same, then we could say that two samples of a gas have the same number of particles. Does that make sense? Yeah, okay. So what that means is that if these two boxes are the same pressure, the same temperature, and they're the same size, they have the same number of particles in them. So we're gonna move forward with that. A guy named Avogadro, who's another chemist, reached the same idea building on the work of Gay-Lussac, who we talked about earlier, and he had been looking at the relationship between pressure and temperature. But these guys realized that when you reacted two gases together, they would combine in simple integer volume ratios. Basically, what that means is you could combine things like 1 to 1, 1 to 2, 1 to 3. You would never be combining things in terms of 1 to 2.5. What you would really be looking at then is 2 to 5. But your ratios are always going to be whole numbers. They're not going to be fractions of a number. Just hang on with me. We'll get there. So with water, we're going to do this reaction. We'll probably do it tomorrow. I just need to set it up for you guys. We're going to take water and split it into two gases. And it turns out you can test it. You can separate water to hydrogen and oxygen, and you can identify what they are because of the way that those two gases behave. So oxygen and hydrogen are both things that are pretty flammable. So we can actually light them on fire, which is pretty cool. So down here at the bottom, I already drew in this earlier today, but here's how we're going to try to figure this out. And this is what early chemists had to do. So if we know that we take 2 volumes of hydrogen and 1 volume of oxygen and get water, then what folks would realize is that you would get, let's see, hold on, time out. I'm going to go backwards. All right, so I'm going to make some water. There actually are colors that people agree to use for different elements. For hydrogen, we tend to use white. For oxygen, we use red. So I'm going to put a water molecule here. So if you know that a water molecule is 2 parts hydrogen and 1 part oxygen, you can kind of make a guess that this is what our molecule should look like. Would we get that right, do you think? Yeah. So what if if we put 1 here, so this is an equation, so the stuff on this side should be the same as the stuff on this side. So I'm going to put 2 hydrogens on this side, 1 on that side. Does that seem accurate to you guys? Okay. So this is kind of how we're setting things up, is that for every box, we're going to put a particle in it, and the particle is just going to represent a uniform volume. So we could pretend like it's a liter or 2 liters or 10 liters, but here we've got 1 volume of hydrogen plus 1 volume of hydrogen, so we have 2 total. 2 volumes of hydrogen plus 1 of oxygen gives us water. Okay, we're going to come back and talk about this in a minute, though, because this is actually not exactly right. All right, I'm going to switch pages. You guys ready? Trying to keep things moving for you guys, because I know it's the end of the day. All right, so I'm going to move these guys off. So what if instead, so now we've got hydrogen and chlorine, okay? Grab some chlorines. So what if we have hydrogen and chlorine? Sorry, we'll go back up one first. What do the HO and the 2 in the chemical formula tell us? Well, every molecule of H2O has 2 atoms of hydrogen and 2 atoms of oxygen. What about another example? What if we have hydrogen and chlorine? And then we get HCl at the end, right? So what if we've got 1 volume of hydrogen and 1 volume of chlorine, and we add them together? What do you think the formula for hydrogen chloride would be? It would just be 1 of each, right? If we take 1 volume of hydrogen and 1 of chlorine, then we get HCl at the end. We're getting really close to being able to write formulas here. Sorry, I'm gonna move my snatoms out of the way. They're all piling up in front of me. So there's our hydrogen and chlorine. How are you guys doing? Are we super confused? Not yet. Okay. Folks got really confused earlier today. All right, the next one. It says represent the reaction where a volume of nitrogen reacts with 3 and forms ammonia. How are we going to do that one? Don't pay attention to this. I needed to really reprint this, and my printer was not working. Oh, Jazz just asked me if I could take a picture. I'm actually recording this, but I mean, I've been having a lot of problems with my cameras. I've been going back and forth with Mr. Suchecki.
Wait, Dr. O, I think I know
what
the answer.
To what? To this?
The question you just asked us.
Okay, what do you think?
Wait, can you say it one more time? Because I had it and
now. What's the formula for ammonia? That one?
So it's 3 volumes of hydrogen, and then no, wait, I don't know.
Yeah, so there's this tricky thing that's happening here. I don't know if you guys have noticed, but if I've got 1 volume of nitrogen and 1, because I'm missing a big thing here, and 3 of hydrogen, and then we form ammonia, what are we going to get? Hold on. I'm going to build it for you. No, this water molecule. So this is actually going to be NH3 on the end. Right, so we're doing okay so far. And early on, chemists did okay with this. And then they realized that they were starting to have a problem because stuff got a little bit more complicated. You guys ready for the complicated part? Yeah. Okay, more puzzles. So what ended up happening? Part 2. Chemists occasionally found that a volume of gas reacted with a volume of gas B and made 2 volumes of a gaseous product. That's a problem.
Early chemists like Gay-Lussac were unable to account for this behavior, but Avogadro's contribution was he reasoned the molecules of some gaseous elements must have two atoms. Have we talked about that before? That some of these guys are they're diatomic? Look at this, they stick together. That's a diatomic molecule there. It has two atoms that are attached. So here's how the puzzle works. What they saw was that, for instance, if you took 1 volume of hydrogen plus 1 volume of chlorine, you actually produced, and we didn't mention this up above, you actually produced 2 volumes of hydrogen chloride, which meant that on this side, right, you had this number of particles plus this number of particles and ended up with this. And see how all these are paired? There's 2 atoms with every single one of those. So here's our 2 hydrogen chlorides. If I put 1 in each to represent that there's 1 on each side, they have magnets in them and they really want to hang out together. If I put 1 chlorine here and 1 chlorine here, no, you can't go over there. Are these equal? Is this side equal to this side?
I say no.
I would also say no. So what do I have to do to make them equal? Can I like cut these in half? Because if I cut it in half, it's not.
Don't you have to get it so that the white ones are together and then the green ones are together too?
Yeah, so what I have to do is I have to say, oh, well, maybe this gas isn't single atoms. Maybe this gas is a molecule that's made up of 2. And then if I want to make the product, I have to kind of switch partners with them, right? Just to switch these around like that. Then I can put them on this side. But when they're over here, they're diatomics. And so there are actually a lot of things. No, they're so sticky. Stop being sticky. I'm about to pull out the big ones. I have a bigger set.
So wait, Dr. O, from like an algebraic standpoint, is that basically like dividing by 2?
So this is going to be H2 plus Cl2 yields 2HCl. So this would be distributive if you want to talk algebra.
Oh, okay.
And this would be, you have 2 H's, you have 2 Cl's, and then you have 2 HCl's. It would be like, if you have 2A plus 2B equals 2. Anyway, yeah. So this is kind of how they figured this out, is they were doing okay with figuring out how to add things and make different things. But then they realized that sometimes you got twice as much volume as you thought you should otherwise. And so that became an issue. So, all right, next page. Having trouble like hiding all my answers from you guys. Okay, so going back to the water thing. Okay, so for water we had 2 hydrogen plus 1 oxygen. And when they actually measured the product, you actually got 2 volumes of product. So if you had 2 of these plus 1 of these, and you got 2 of these, you'd have to figure out that math again. So our water, now we need 2 waters over here. The waters tend to behave themselves. So I've got 2 volumes of water over here. I can't have just 1 oxygen and just 1 of 2 hydrogens, right? That doesn't work. The math doesn't add up because I need to double my particles on this side. And so these guys too, these guys are also going to be pairs. Does that make sense? I know they're all sticking to each other, but there, they can all hang out together over there. But now I've got 2 red and 4 white over here, and 2 red and 4 white on this side. All right, how are we doing? So far, so good? So this is what chemists had to do. They had to do a lot of reactions and test these things and measure what was happening on the other side to try to figure out these things about these gases. Oh, sorry. Come here, nitrogen. Ugh. My bigger snatoms are on the floor. I'm wondering if they would behave as badly. All right, so what about the last one? I don't have enough SNATOMs to pull off the last one. So this question here, why do molecules of oxygen have to have an even number of atoms? Because reactions that form water are always going to be two particles of product for every one particle of oxygen. Oops, sorry. You're going to have 2 particles of product for every 1 particle of oxygen. So that tells you that this oxygen molecule has to have 2 oxygens with it because they're going to break apart from each other to form the product. Do you guys have any questions so far? All right, ready for the last one where it gets trickier? So if we've got 2 volumes of nitric oxide, only we're going to change it up a little bit, and instead of just 1 particle, we're going to have 4 particles in there. And then we have some oxygen. And we know that we get how many? Sorry, I'm going to peek. And then we get 2 volumes of product. What is our product going to look like? What's it going to look like? One way to kind of approach this sort of problem is imagine that you're going to start with these things and then you're going to divide the stuff up into it. Oh, some of you guys made a face at me. So I'm just going to start. I'm just going to start with these guys. And say, okay, well, I'm going to put 4 of those in each of these boxes. And then I'm going to take my oxygens, and I've got 4 molecules. So if I've got 4 molecules here and 8 molecules here, I can't just take this whole thing and stick it onto one of these. I'm going to have to divide them up. So I've got 8 atoms of oxygen here. So I'm going to take those 8 atoms and divide them evenly among these other molecules. Because remember, we said that a reaction's happening. So they're actually going to actually bond together and form a bigger particle. So I'm just going to move one of those oxygens to each of these guys. I always think that these look like flies every year. There we go. What do you guys think? Do you guys have any questions? No. How are you guys doing today? Go ahead, Mia.
For this one, wait. And okay, wait. Yeah. Okay. That one doesn't make sense. Like, why isn't there 3 white ones at the end?
What do you mean?
Or 3 oxygen? Like, why is it only 2 oxygen?
Here?
No, in the reddish gas.
Because
isn't there like a 1 kind of next to this ANO? Like, isn't there a sub 1?
I'm not sure what you mean.
Like, I don't understand why it's only 2 oxygen at the end and not 3. Because wouldn't it
Here?
be... Yes.
Because this means that each one of those molecules has 1 nitrogen atom and then 2 oxygen atoms. I'll zoom in. So these red ones are the oxygens and the blue ones are the nitrogen. And so each of those is made up of 1 nitrogen. So you just have N. Sorry, can't see that. So the 1 is implied. Like usually if it's just 1, we don't write it. And then the O2 means that each one has 2 oxygens. So 1, 2, 1, 2, 1, 2, 1, 2.
Okay.
1, 2, 1, 2, 1, 2, 1, 2.
Okay.
And I'll tell you what, it's okay if this doesn't feel super comfortable today, because we're gonna come at this a couple of different ways.
Okay.
So we'll circle back around to it later this week. What do you guys think? You all look like you've had a long day of online school. Grace, go ahead.
Would you be able to show the page that has 3 through 5 again? You're just cutting out, so I want to make sure that I have all of the things
Yeah,
written
yeah.
down correctly.
Well, which part do you want to see? Because I didn't write everything down.
Just like the final answer for number 3 and 5.
Number 3 and 5. Okay, so this looks different because it's how I wrote it. Well, I can do it like this. Hold on. So what we said for number 3 was, this was before we knew how many volumes we had on the other side. So if we've only got 1 hydrogen and 1 chlorine, we would expect that our product looked like that. 1 hydrogen, 1 chlorine. And that works. And then for number 5, which is hydrogen and chlorine again, but I guess I could use this. So what actually was figured out is that if you measure the volume of the product that you get when you combine hydrogen and chlorine, you actually get the same volume that you start with 1 volume here and 1 volume here, and you end up with 2 volumes. Then it can't be as simple as you add 1 hydrogen to 1 chlorine and get 1 volume of something. What that has to be telling us is that we start out with a diatomic hydrogen, so something that has 2 atoms. And then we have a chlorine that also has 2 atoms. And the reason we get 2 volumes on the other side is because we're going to split those and switch their partners and end up with that. Does that make sense? So we're going to do this a couple of different ways before we're done with the unit. So if today you're like, it kind of makes sense, but I need more practice with this, then that's a good spot to be in. So I just wanted to go through that worksheet with you guys today. So I'm not going to keep you all the way till 2:30. We can chat if you'd like to. If you feel like you want to be productive for the next 6 minutes, I would recommend you work on your science fair research plan. Woo! No, you guys look like you've had a long day. All right, so if you'd like, you can go ahead and log off, and I'll see most of you tomorrow.
Doctor, I have a question about yesterday.
What's up, Tammy?
So what else did you guys talk about?
What did we talk about yesterday?
Yeah.
Mixtures and solutions. So if you look at worksheet number 1, all my papers are all mixed up right now. I don't know what page I'm on. So on worksheet number 1, we talked about filter funnels and distillation. And that if you wanted to separate something like sand and salt, you could do it if you added some water to it to dissolve the salt, run it through a funnel to remove the sand, and then evaporate the water out of your flask to get your salt back. The way that you could do distillation is if you had something dissolved in a liquid here, you can put your saltwater solution there, warm it up, and then this is going to make your gas go up into this condensation tube. Normally this tube has cold water on the outside, so it's a little bit chillier than the rest of the room. That gas would condense in this tube and then drip out into a flask. And so you'd ultimately be left with whatever was dissolved in your stuff here and your solvent here. You could do this with 2 different liquids too. So this is how they make alcoholic beverages. You distill out the alcohol and collect it on the other side. For number 2, it says it would be more how could you separate, or why wouldn't the filter funnel work for salt and sugar? It's because they're too similar and their properties are similar. So you wouldn't be able to separate them by dissolving one and not the other, because both of them would dissolve. And so you would have to come up with something a little bit more complicated to do that with. I'm actually not sure what it would be. There we go. We also drew particle diagrams for iron filings and sulfur together, and I actually had iron filings and sulfur in class.
and then we mixed them together and separated them with a magnet, which is very messy. I had sulfur all over me the rest of the day. It was all over my pants because the dust kept coming off. If you make a compound of it, you actually have the two sulfurs connected to every iron, and that actually forms a mineral called pyrite or fool's gold.
Do colors matter?
Not really. I mean, these are colored because chemists made an agreement to do that. So the black is carbon, this is nitrogen, oxygen, sulfur. These are hydrogen. The green ones are halogens, and the purple one is like phosphorus. It's got a special one. So some of them like kind of matter, but nobody really. There's no like you drew your molecule the wrong color police. How's that? If you were drawing molecules with a computer program, it would automatically make them certain colors. So normally when you see a publication, they're that way. Like water's always this red and white combo, right? And that's because it's oxygen and hydrogen. The reason that you can use a magnet to separate things from a mixture but not a compound is because the attractions between the iron and the magnet are strong enough when it's alone to be able to separate them. But in the pyrite, the attraction between the iron and the magnet is not greater than the attraction between the iron and the sulfur and the other particles. So you won't be able to separate them that way.